This is Duzi, and this is my first video. Thanks for watching. In this video, I'm going to continue with the topic inline constexpr template. In the last video, I talked about using inline constexpr to customize your library. And in this video, I'm going to demonstrate more usage of constexpr value like this, looking like this. So the point is an inline constexpr template could be specialized like a template class, like a template class. A template class could be specialized, for example, in specialization, and have its own definition in the class. Inline constexpr value is the same. We can give different type a different value. So if it's a int, for example, if it's an unsigned, by default we give it a 0. For example, in we give it a this would be a better example. And we give it more example. It looks very similar to template class specialization. I write an example to use it. A good example for using a constexpr value is that we can use the constexpr if statement. Looking like this. Constexpr if statement is compiled as is evaluated at compile times. For example, if we say if size let's say they give it a parameter. If size equals, let's say 1, no, 4, then we do something here. If not, we do something else. Let's say it's a check size. Okay. Let's do some checks. Give it char and give it a full type. Char. Okay. Full char. Full int. Oops. Well, this is a simple example. It actually does nothing. Just check the size, and if the input size is 4, then we say size is 4, which is good. If not, we say size is not supported. To demonstrate how we can use inline constant expert and the if constant expert, we can actually make it constant expert. So that these checks are actually done at compile time. So let's see how it runs. Okay, let's see what's happening. Okay, we have to include see. So this is 4. Boolean is not supported, Boolean is not supported, char is not supported, in is 4. Full char, this is 4. This is not supported, not supported. Well, when you want to extend it, we say that if we do this, then the last one will be 4 again, will be 4 2. See? We can also do this for char. Yes. Let's put some size out. And short. But this is not defined. Not having a size specialization. So 0. Give some more types. Zero, 0. This is 0 2. Full long is 0 because we don't have a size specialization for full long. Short is 0 2 because we don't have a specialization for short. This is long is A because it's size long and we have the space. See? So this is the simple example showing how a inline constexpr value is specialized for different types and how it could be used in a if constexpr statement. We can say that if this is size is larger or equal than 4, and do something else. This is very similar. Well, comparing to Matter is somehow a inline context per expression value could be used to replace meta programming types. In meta programming, we have some meta constants. For example, like true types, false type. They are integral. Alright. These are coming from the defined by standard. The standard meta element could be used for general purpose meta programming directives. And these types are actually very similar to this inline constant expert. If we use it for meta programming, we can actually use it in a similar way. If we use the meta programming way, for example, by default, we give the size value is 0 because we don't know if this is similar to this one. And if we give some more, so long. And let's see the similar things. See, this is very interesting. Meta size bool, we have a specialization for it, so it's size 1. Meta size int, we don't have a specialization, so it has no size, 0. And full int is 4. So as we can see that constexpr value is very similar to type specialization. But we can actually define size, okay. 0. Say for example, let's say 1, give it 1. Let's say 4. Okay, we have to include the type char, type chase file to make it work. Oh, alright. It's in the namespace. See, it's similar. This is the meta programming element, integral constant. The similar thing is the bool constant. A bool constant is actually an integral constant. A bool constant have its true type and false type. For true type, it always gives us a true value, which is 1 as an integral, and false type, which is 0 as an integral. A metaprogramming element types could actually used for it's very useful in a meta algorithm. A meta algorithm is in C++ is an algorithm using template, using class template or maybe inline constant constexpr value template. For example, if we can say that, let's see, we use a full value, okay. By default, we give it a we can give a full type, a specialization, a full value, say true type. If it's true type, maybe we give it 10, for example. And if it's a false type, give me one, okay? Just for an example. We can also specialize for integral. Well, this one is special because it is a partial specialization. We still have a t. Same. Okay, we give it a different. Okay, let's say it's 1, it's 2. False type is 1, type is an integral type. This is 3. Yeah, it's not very interesting. But the demonstration how a specialization could be used as a compare time evaluation, compare time state checks. If we give full value a type parameter, it will check it's like a dispersion, like a overload, like a value overload when calling a function. When it is a false type, it gives us value 1. When it is a true type, it gives us value 2. An integral, any other integral type, it gives us 3. So this is very similar to function overloading. Say, and alright, integer. Let's give it an int. See, this is very interesting. If used in a real project, this will be very interesting approach. Let's see. Let's do some. We can make some usage. Full value. Let's say int. Let's see. Let's say int. Okay. In Let's make it dynamic. Okay. Okay, let's see what's happening. Alright. Boolean constant. Oh, we need to revoke the value. Okay, let's see. Alright. See, integral type is 1, 2, 3, 10 plus 1, 11, 10 plus 2 plus 3. Yeah, this is very interesting. Fourth type is 1. Two type is 2. Well, the example is not very interesting, but a quick demonstration of the usage for inline context per template value and comparing to the metadata type, like integral constant, bool constant, true value, and the specialization usage, specialization for types, specialization for value, for context per value, and yes, and the conditional branch. It's a compile time conditional branch. Well, this is very useful. Let's give another example for compile time. For compile time conditional expect statement, let's say auto. Okay, give type. Recommend value type. Okay, recommend value 4, and we can say that if context per the size of the type equals 1, which is 1 by size is known, 1 by length size is known, type is known, and size is 1 by. Then we give a byte value. We give it a byte value, okay? By 128. If context per size t equals a, type is known and size is A. Let's give it a long. Okay, make it simple. Make it simpler. Okay. Otherwise, we give it a false type. Let's see how it works. Bool, okay. And give it some types. Bool, char, in, long, char, in, long, and full in. Let's see. Embedded operands to binary expression. Oh, right. If it's a byte cannot let's short, okay. See what's happening? 1 byte, boolean is 1 byte, boolean size is 1, and it gives us what? 128. If it's 4 is not recognized and give us different. Let's see this. This is the most interesting one. Which is 1, 4. A boolean type is 1. Well, this demonstrates that in a constexpr if statement, the function retains different type according to different if based on the checks. So in this case, it gives us short return type. And if the size is A, it gives us a long return type. Otherwise, it gives us a boolean value. So this is very useful, another useful case for constexpr. Other cases, let me see. Yeah, configuration for library classes. Well, all right. Maybe there's another use cases. In this video, this is all. Thank you for watching. That's all.